Have you ever thought about how the games we play, even, simple ones, could hold a secret key to understanding how we learn? Especially for those of you coming from elementary education, with that incredible focus on how young minds grow and explore. Well, the world of game-based learning is absolutely bursting with potential. Today, we're pulling back the curtain on something truly transformative: learning analytics and educational data mining. These powerful tools are fundamentally changing how we design and understand educational games, making them more effective than ever. Think of it as giving us like X-ray vision to the learning process.
That's a great way to put it. Our mission today is to take a deep dive into this fascinating world where education meets big data. We're going to unpack how designers use information gathered from games to make them not just fun, but incredibly effective learning experiences.
So it's more than just engagement.
Oh, much more. Think of it as a shortcut to becoming truly well-informed about the cutting edge of educational games, especially relevant for elementary settings. You'll gain insight into how the very best learning games are built, refined, and personalized for young learners.
And we're drawing on some solid research for this, right?
We are. Our guide for this exploration comes from a comprehensive handbook chapter. It's titled Learning Analytics for Games by V. Elizabeth Owen and Ryan S. Baker. It's a really insightful piece that lays out the foundational methods and their applications.
Okay, fantastic. And what a guide it is. So maybe lay out the roadmap for us. What are we covering today?
Sure. We'll start by defining what learning analytics and educational data mining actually are, explore why they're so crucial. Then we'll get into these 5 superpowers or core categories of analytical methods. Each offers a unique lens, like you said, for that X-ray vision. And finally, we'll see how these powers are used throughout the different stages of developing a learning game.
Giving us that fresh perspective on how games can be incredibly precise educational tools sounds great. Let's get started on this deep dive.
Okay, so let's begin by defining these core concepts. Learning analytics, or LA, and educational data mining, EDM. They're often discussed as a converging set of methods.
Converging. So they're similar, but maybe not identical.
Exactly.
Yeah.
While they originate from slightly different research communities and might ask subtly different research questions, LA traditionally focuses more on real-time understanding of learning processes, to inform immediate interventions.
Like what's happening right now with this student.
Right. Whereas EDM tends to focus more on discovering broader patterns and predictions within large historical data sets, finding the bigger trends. But honestly, for our purposes today, we can largely think of them as interchangeable.
Okay, that simplifies things.
Yeah. They represent a host of education-specific methods for exploring and mining these large streams of data that come directly from educational contexts. And importantly, they're not just general data science applied to education. They're increasingly developing unique, bespoke tools for this specific domain.
That's an important distinction to clarify. So these aren't just tools for academic researchers to, ponder in their ivory towers, are they? It sounds like they have a very practical application.
You've captured the essence perfectly. No, these are practical tools designed specifically to enhance learning design and ultimately outcomes. For you in elementary education, think of this as a way to move beyond just guessing what works in a game or even any digital learning tool.
Right. Less intuition, more evidence.
Exactly. Moving towards knowing based on actual observable student interaction. It shifts the paradigm from intuition to evidence, offering a level of precision we've, frankly, rarely had in understanding learning.
That sounds like a monumental shift. But okay, why is collecting data from games specifically such a big deal for learning? I mean, a game is just a game, isn't it? What makes it such a rich source compared to, say, a digital worksheet?
That's a great question, and it gets right to the heart of the big data aspect. Digital games are inherently designed to generate what's called event stream data.
Event stream data?
Yeah. Every single click, every move a player makes, every decision they choose, every incorrect attempt, every successful completion, all of it gets captured as a data point.
Wow. Everything.
Pretty much everything meaningful to the interaction. And this isn't just a handful of records. It's truly big data, gallons of it. When analyzed, this continuous stream of interactions provides incredibly rich, granular insights into playful learning patterns. This richness is what supports data-driven design.
So it's not just about whether they got the answer right at the end.
Not at all.
But how they got there, what they tried along the way, and when they struggled or succeeded.
Precisely. Imagine a digital spelling game, maybe for first graders learning phonics. A traditional assessment might just give you a final score, how many words they spelled right.
Standard quiz, yeah.
But with event stream data, the game records every letter they typed, every time they used a hint, every deletion, every time they rearranged letters, every incorrect attempt. It logs the time between actions.
So much more detail.
Far more. It allows designers, and potentially you as a teacher looking at a dashboard, to understand the process of learning, the strategies students are using, and the specific points of confusion, not just the final outcome.
It's like watching a high-speed replay of their thought process, almost, moment by moment.
That's a fantastic analogy.
Wow! For an elementary teacher, this truly is like having an invisible assistant, observing every single student's precise learning journey within the game. It tells you not just if they learned, but how they learned, where they stumbled, what strategies worked for them. That's a huge leap from just seeing a score on a report or a completed worksheet. It allows us to apply that X-ray vision we talked about.
Couldn't agree more. And this level of detail is exactly what makes these analytical methods so powerful.
Speaking of powerful, the source breaks down these methods into 5 main categories. You call them superpowers. Think of them as different lenses, right? Different ways to use that X-ray vision.
Indeed. These 5 superpowers of learning analytics are prediction, structure discovery, relationship mining, discovery with models, and visualization. Let's delve into each one. Maybe start with prediction.
Okay, let's start with prediction. It sounds like it does what it says on the tin, but I'm sure it's more nuanced than just guessing the future. What exactly is prediction modeling doing for us here?
It is more nuanced, yeah.
Yeah.
Prediction modeling is all about inferring an outcome or a measure of interest. We call that the predicted variable from a set of input data, the predictor variables. Essentially, it creates a mathematical model, a model that can forecast future outcomes or maybe assess current variables that are just hard to measure directly.
Like how engaged a student is.
Potentially, yes, or how likely they are to succeed on the next level. It identifies strong correlations between observed behaviors and desired outcomes, and then uses those correlations to forecast future events or hidden attributes.
So it's like a smart algorithm that can anticipate student needs, almost like a digital crystal ball for learning. That sounds incredibly powerful.
A very apt analogy. And there are a few common types of prediction you'll see. First, there's classification.
Classification.
Yeah, it predicts a binary outcome, like yes, no, or maybe a multi-category outcome. For example, predicting if a student will pass or fail a certain level, or even which broad learning style they might align with based on their in-game choices.
Okay. Pass, fail, category ABC, got it.
Second, we have regression. This predicts a numerical value. So predicting a student's score on a level, or maybe how many attempts they'll need to solve a puzzle, or even how long they'll take.
Predicting a number, basically.
Right. And third, there's something called latent knowledge estimation. This tries to assess student knowledge, often as a probability, say between 0 and 1, based on their correctness data during play.
So not just right or wrong, but how much they know.
Exactly. It estimates how deeply they understand a concept, maybe even how confident they are in that understanding, based on the pattern of their answers.
Okay, let's unpack this for the elementary classroom. How does this superpower actually help teachers or game designers right there on the ground with young learners? What's the practical benefit?
Well, it's incredibly powerful for early intervention. That's a key application. Imagine a math game. Maybe it's teaching addition with regrouping.
A tricky one for second graders sometimes.
Definitely. Now imagine the game, based on a student's initial interactions with simpler problems, predicts they are about to get stuck on regrouping before they actually fail a bunch of problems or get visibly frustrated.
It sees the struggle coming.
It anticipates it. And this allows the game, or maybe even an alert pops up for the teacher on their dashboard, to offer support proactively. A hint, a different explanation, maybe a simpler practice problem.
Wow.
It can also dynamically drive personalized learning paths. So the game adjusts the difficulty or the type of problem based on these predictions, ensuring each child gets the right challenge or support at the right moment. It's about being proactive, not reactive.
That's a game changer, literally. So no more waiting until the student gives up or gets a string of answers wrong. The game can sense it coming, give them a nudge. Can you give us another concrete elementary example?
Certainly. Think of a science game. Maybe students are virtually building simple circuits to understand electricity. First, second grade level. Prediction modeling could identify a student who is likely to struggle with connecting components in series versus parallel, just based on their early choices, maybe how they handle polarity, those basic concepts.
Based on those initial clicks and drags.
Right. The game could then, in real time, offer a targeted mini-tutorial, or even a simpler, guided activity just on series circuits, before the student gets totally bogged down in the more complex parallel stuff.
Smoothing the path before they hit the wall.
Exactly. Or consider a game for early literacy skills, like phonological awareness. Prediction could flag which students are at risk of struggling with rhyming words. Then the game could automatically present more explicit phonics exercises, or shift to a level focused entirely on auditory discrimination. It prevents that frustration and ensures those foundational skills are solid, keeps the learning relevant and within their zone of proximal development.
That's just a smarter way to keep kids in that learning sweet spot and prevent those early academic setbacks. Okay, really powerful stuff. Let's move on to our second superpower, structure discovery. What's this one all about? How does it differ from prediction?
Structure discovery is quite different. Prediction is about forecasting a known outcome. Structure discovery, on the other hand, attempts to find hidden patterns or, well, structure in the data without an a priori idea of what should be found.
So you're not telling it what to look for.
Not specifically. It's about letting the data itself reveal its natural groupings and relationships. It's more exploratory. Like being a detective and letting the clues form the story themselves rather than starting with a suspect.
So it's like finding hidden tribes or natural categories within the data that we didn't even know existed. That sounds fascinating.
That's a great analogy. One key method here is cluster analysis.
Cluster analysis.
It automatically groups similar data points together into clusters. It's super useful when you don't know the categories beforehand. It lets the data show you how students naturally group based on their behavior.
Can you give an example, maybe with that fractions game you mentioned earlier?
Absolutely. So in an elementary math game like SavePatch, which the source mentions was used for teaching fractions cluster analysis, could group students by the strategies they use to solve fraction problems, even if those strategies weren't explicitly programmed into the game as options.
So it discovers strategies the designers didn't even anticipate.
It can, yes. It might reveal, for instance, a cluster of students who consistently use a specific, incorrect, but common strategy, like always adding the denominators instead of finding common ones.
Oh, I've seen that happen.
Right. Or maybe always simplifying before trying to find a common denominator, which might lead to more errors in complex problems. This direct insight, coming purely from the data patterns, can then inform game design revisions. Maybe add a hint about denominators or change a level to specifically address that misconception.
That's really targeted feedback for the designers.
It is. And another powerful application is identifying emergent groups of players. The data might cluster players into types like achievers, who focus on scores, explorers, who try everything, or maybe disengaged players based on their actual play styles. This was seen in a game called Physics Playground. It helps designers understand who their players are, beyond just scores.
That's brilliant. It's uncovering the how and who behind the numbers, giving us a much more complete picture of our learners. What about domain structure discovery? That sounds a bit different.
It is. Domain structure discovery automatically finds the inherent structure of the content itself within the game. Not the players, but the material.
Okay, like the relationship between different skills.
Exactly. It can be used to determine which problems involve the same underlying skills or concepts, or, crucially, to identify prerequisite relationships. For instance, it can uncover that mastering concept A seems to be necessary before students can successfully master concept B.
So, in an elementary context.
In an elementary reading comprehension game, this method might discover that certain vocabulary words are consistently mastered only after specific phonics skills are understood. Like, you need to know the she sound before you can reliably decode ship. Or it might show that understanding one story element, like identifying the main character, is usually a prerequisite for grasping a more complex element, like the character's motivation or the story's theme. This helps map the learning landscape within the game, ensuring a logical skill progression.
Making sure you don't ask kids to run before they can walk, basically.
Precisely. And finally, under structure discovery, we have network analysis. This sounds like it's about connections, but what kind? Network analysis investigates complex networks of relationships between data points. It's often used for understanding paths or flows through a system. Think of analyzing the paths a student takes through a digital maze game designed to teach spatial reasoning or planning.
Okay, like the route they took.
Yeah. Network analysis could identify common successful paths versus common dead ends or loops where students get stuck. This helps designers refine the puzzle, maybe make the successful path clearer, or offer hints more effectively when someone enters a known dead-end zone. It can also shed light on how students navigate something like a level selection menu. Are there levels everyone clicks on first? Are some being ignored? That helps improve the user interface.
So it optimizes flow, whether it's through a level or through the game's menus.
Right. Imagine a social-emotional learning game where students make choices in a story. Network analysis could reveal common decision pathways that lead to positive social outcomes versus those that lead to conflict, allowing designers to subtly guide students toward more empathetic choices, maybe by making the consequences clearer.
That makes so much sense. It's about seeing the flow of learning and decision-making within the game. Okay, superpower number 3, relationship mining. This sounds like it's a more direct way of connecting behaviors and outcomes than structure discovery.
You're right. Relationship mining is, well, just as the name suggests, about discovering explicit relationships between different variables in large data sets. If X happens, does Y tend to happen too? It's actually one of the most common categories of educational data mining research because it's so broadly applicable and offers immediately useful insights.
Okay, so how does it work? What are the methods?
First is association rule mining. This is where the software automatically finds if-then relationships. If one variable or value pair is seen, another usually accompanies it.
Like, if students do A, they also tend to do B.
Exactly. For example, the data might show if a student frequently uses the hint button, the if, then they also tend to complete the level successfully, the then.
Ah, suggesting the hints are actually helpful.
Right, maybe they're using them strategically. Or in a kindergarten math game focused on number sense, if a student struggles with basic number recognition, like matching 3 to 3 dots, then they often also struggle with simple addition problems involving those numbers. This helps designers understand these common patterns of behavior, how different actions or skills are connected. It allows them to potentially address the root causes of difficulty more effectively.
That's incredibly practical for game design, almost like finding a behavioral fingerprint that helps you optimize the game. What's next in relationship mining?
Next is sequential pattern mining. This is similar to association rules, but with a critical addition. The then part must occur after the if part. The order matters.
Ah, so it's about the sequence of events.
Precisely. This is powerful for understanding the precise sequence of actions a student takes, especially leading up to success or failure. For instance, a game might discover if a student attempts a specific incorrect strategy for a math problem, like clicking random answers repeatedly, then they typically follow it with a period of disengagement or several more incorrect attempts.
So you see the downward spiral starting.
You can pinpoint it. And knowing that sequence can inform when and how to provide interventions. Maybe offer a hint after the second random guess, but not the first. The source mentions how engrams, which are just sequences of play behavior, are used to tailor adaptive level progression in some games and also to analyze common play patterns in elementary math games.
So you could spot, say, in a phonics game, that if a child misidentifies the short A sound, then they tend to guess randomly on the next few vowel sounds.
Exactly. And that specific sequence could trigger a targeted mini-lesson just on vowel sounds right when they need it.
Timing the support just right, based on their precise journey through the game. Anticipating the moment they're about to derail. Any other relationship mining methods we should know about?
Yes, briefly. There's correlation mining. This checks a large number of variables for statistical relationships. Do they tend to go up or down together? For example, finding a negative correlation between confusion and achievement in a physics game. More confusion, lower scores. It highlights general trends. And finally, causal data mining. This one is a bit more debated, but it aims to use patterns of covariance to see if one event statistically seems to cause a later event, moving beyond just correlation towards potential causation.
Okay, so all these relationship mining methods help us understand how different actions and outcomes in a game are connected, even the order in which they happen. This lets designers tweak game mechanics to encourage positive learning behaviors and pinpoint potential confusion spots that might not be obvious otherwise. It's about fine-tuning the whole learning ecosystem within the game with incredible precision.
Exactly. It's about building a more responsive and effective learning experience based on empirical evidence, moving from just intuitive design to a truly data-driven science of learning game development.
Let's move to the fourth superpower. Discovery with models. This one sounds a bit meta. The name implies using models you've already built. So it's like building a special lens using one superpower and then using that lens to get even deeper insights with another superpower.
That's a perfect way to put it. Yes, discovery with models involves a multi-step process. First, A variable or set of variables is created through another LA or EDM method like prediction, or maybe clustering from structure discovery, and then that newly created derived variable is used in a second analysis. So you're building a more sophisticated, nuanced variable first.
Like a variable for frustration or engagement.
Exactly, things that aren't directly measured by clicks. You model that state first. Then you use that modeled variable, that frustration score or engagement level in a subsequent analysis, maybe correlation mining or prediction, to get deeper insights than you could from just the raw click data alone.
It's like building a custom filter before you analyze the picture.
A great analogy. It allows for much more nuanced investigations. For example, you could build a model of student disengagement within a game, maybe based on patterns like long pauses or repetitive non-productive actions. Then, you use discovery with models to study how that disengagement variable correlates with eventual student success or failure on the level. This provides richer insights than just looking at raw pause times.
Can you give us an elementary classroom example to make this really stick? Show how this two-step process reveals something truly insightful about young learners.
Certainly. Imagine a digital storytelling game where primary students construct narratives. They choose plot points, character actions, maybe add dialogue.
Yeah.
Now, directly measuring something complex like creativity or deep engagement with the story just from clicks is really hard, right?
Yeah, very subjective.
But you could first use, say, prediction modeling or maybe some structured discovery methods to build a model of student creative output. Perhaps this model predicts whether a student's story structure is highly original or just follows a common template based on their sequence of choices and combinations. This creative output score then becomes your new derived variable.
Okay, so step 1, model creativity.
Right. Then step 2, you use discovery with models to study how that creative output variable correlates to other things. Maybe how long students choose to spend revising their story, or the richness of their vocabulary used, if the game captures text input, or even their verbal articulation about their story after playing. If you find a strong link, for example, if higher model creative output strongly links to greater persistence in revising the story and richer post-game descriptions, then designers have evidence that the game mechanics are successfully fostering creativity.
Wow. So you can start to measure and understand those really subtle but crucial underlying learning states like creativity or deep engagement that are so important for young children's development.
Exactly. It lets us analyze complex, indirectly observable constructs and understand their impact on learning behaviors, going beyond just surface-level data.
That's truly next-level analysis. Okay, and now for our fifth and final superpower, which often seems to be where the aha moments really kick in. Visualization. This is where the data really comes alive, isn't it? Makes it understandable.
Absolutely. Visualization is described beautifully in the source as the distillation of data for human judgment. Its whole purpose is to express complex data visually in a way that makes patterns easy to spot. It makes large amounts of information simple and digestible.
It takes the abstract numbers and makes them tangible.
Precisely. It's what allows teachers, designers, even the students themselves sometimes, to intuitively grasp what's happening in the data.
I can totally imagine how seeing a visual representation, a chart, a map, could immediately reveal patterns that rows and columns of numbers just hide.
That's exactly right. And visualizations are crucial at all stages of game development because they provide those immediate intuitive insights. There are many types, of course. Simple descriptive statistical charts, learning curves showing progress over time, heat maps, radial visualizations, network diagrams showing connections, state-space diagrams showing paths. Each offers a different perspective.
Let's dive into some elementary classroom examples from the source, because this is where it gets really impactful for educators. What can heat maps show us, for instance, in a kid's game?
Heat maps are fantastic for spatial data. Imagine a map of your classroom's virtual learning game. Maybe it's a digital scavenger hunt around a virtual museum designed to teach history concepts. Heat maps can visually show areas where students spend a lot of time maybe indicating interest or maybe confusion. They can show hotspots where they get stuck or where they fail frequently.
Like a thermal camera for student interaction.
That's a great way to think about it. The source mentions research where heat mapping combined with surveys helped identify areas of frustration and high failure in a game, leading to design changes that boosted performance and engagement. For an elementary teacher using such a game, you could potentially see exactly where students are getting lost or frustrated on that virtual field trip and maybe add a clearer signpost or simplify a task in that area. SimCity EDU use heat maps effectively to show high traffic areas, helping them place critical resources optimally within the game world.
That's incredibly specific and actionable feedback. Okay, what about network diagrams and state space diagrams? You mentioned paths earlier. How do they help us see the learning journey visually?
These are excellent for showing the paths players take through game levels or content. Imagine a diagram showing every possible path a student could take through a story-based learning game. Maybe one teaching problem solving through narrative choices. The diagram could highlight the paths that frequently lead to success versus those that commonly lead to confusion or quitting the game.
So you can see the garden paths versus the dead ends.
Exactly. The Institute of Play used state space diagrams to show common student paths through the simulation space in SimCity EDU. This can quickly identify bottlenecks where students often get stuck. Once you see that bottleneck visually, designers can refine the puzzle there, add scaffolding, or maybe make the goal clearer at that specific point. It helps optimize the flow.
And what about visualizing a student's actual learning journey or progress across multiple concepts, making their growth visible?
That's where progress visualizations come in, and they're super important for motivation, especially with younger kids. Researchers have used things like radial sunburst visualizations. They look like a multi-layered pie chart to show different player strategies across multiple levels of science games, like Fold It. They can reveal info about time spent, performance, tool usage, all in one graphic. And more directly relevant to motivation, the source highlights a fractions game. We're showing students a simple summary screen of their progress at key points, maybe paired with reward points, they call them brain points, resulted in greater student retention and persistence.
So the visualization itself becomes a motivator.
Absolutely. Imagine a child playing that fractions game, and after a few levels, they see a clear, colorful, visual summary of their progress. Maybe it shows which fraction types they've mastered or how many brain points they've earned. That visual feedback directly supports a growth mindset, encouraging them to keep going. Even big commercial games use progress bars and tech trees for this reason.
That's so important for elementary students who really benefit from seeing their progress and getting that encouragement. Can these visualizations even go beyond a single game, like help us understand a student's broader learning profile across different subjects or games?
Yes, there's work being done on cross-game visualizations. Tools like PlayTracer aim to create generalized heat maps that can compare play styles across different games. Others have developed tools that visualize progress using a standardized shape or glyph, allowing educators to potentially see desirable progression or patterns of failure consistently across various games a student might be using. This could help build a broader picture of a student's learning strengths and weaknesses across a suite of educational tools.
This is truly comprehensive. Are there even visualizations for things like, well, how a student is feeling or what they're paying attention to? That sounds incredibly advanced, almost sci-fi.
It's definitely cutting edge, but yes. Building on basic game interactions, visualizations can illuminate patterns related to biometrics. Eye tracking data, for example, can be visualized as heat maps. These show exactly where students are focusing their gaze on the screen during gameplay. Research found low performers in a physics game often focus too much attention on irrelevant parts of the screen compared to high performers.
Wow, so you can see if they're literally not looking at the important stuff.
Yeah, exactly. That immediately tells you something might be wrong with the visual design, or the student needs guidance on where to focus. And in truly advanced research, people have used cortical measurements, brain activity during gameplay. Heat maps of brain activity in a fractions game revealed patterns similar to traditional math activities. These biometric visualizations, used carefully alongside other data, can help test cognitive engagement early in design.
That's incredible, literally getting a glimpse inside a child's brain as they play. And can you even replay a student's journey? Almost like watching a movie of their learning?
In a way, yes. You can distill that complex event stream data into more human-readable formats. One way is through text replays. These essentially create a short, written summary or snapshot of a student's journey through a tricky problem or section of the game, highlighting their key choices, where they struggled, where they succeeded. It makes evaluating specific player behaviors much easier for a human analyst or teacher. These kinds of descriptive visualizations also set the stage for building more complex models later on. They are invaluable for pinpointing exactly where and why a student might have disengaged or become confused.
Okay, so it's clear these 5 superpowers, prediction, structure discovery, relationship mining, discovery with models, and visualization, they aren't just used in isolation, are they? They're most valuable when integrated right into the process of making and refining these educational games. It sounds like a continuous feedback loop, where that X-ray vision is constantly being applied.
It is, and that's the absolute core of what's called data-driven design in this context. It means using these analytics throughout the entire game development process, often within what are called agile game development cycles. From the very early concepts right through to the final release and beyond, you're constantly collecting data, analyzing it, and using the insights to improve both the learning effectiveness and the player engagement.
And this doesn't replace talking to kids or observing them play, right?
No, not at all. It strongly complements qualitative research methods like observations, think aloud protocols, where kids talk through their process in interviews. You get the what from the data and often the why from talking to the players. It creates a much more comprehensive understanding. The key is that designers are continually asking, okay, what did the data tell us this week? How can we use that to make the game better?
Let's break it down by stage then. What happens in the early development, the alpha phase, when a game is still pretty rough, still in its infancy? What are analytics used for them?
In the early alpha stages, the main focus is really on two things: defining a strong learning data framework, deciding what data you need to capture to measure the learning you care about, and using basic data collection, primarily visualization, to understand those initial player interactions.
So mainly seeing what works and what doesn't at a basic level.
Exactly. This early analysis helps uncover fundamental issues. You're looking for obvious bugs, bottlenecks where almost everything gets stuck, how players are interacting with the core game mechanics, or are they even using the main feature, and any glaring user interface, UI or user experience UX problems. Is a button too small? Is an instruction confusing? The aim is to get the basic scaffolding of the game right, and crucially, to ensure the data being collected is actually meaningful and clean enough for later analysis.
So if the game is still a bit rough around the edges, this helps smooth things out quickly and make sure you're actually measuring what you intend to measure later on.
Precisely. It's about setting that strong foundation. And a critical part of this, as mentioned in the source, is having a design-aligned data collection framework. Something like ADJG, that's the Assessment Data Aggregator for game environments. What that means is ensuring the game mechanics that produce the data are clearly linked to the learning objectives. If your game aims to teach early number sense, the data you collect should directly tell you about a student's understanding of quantity or numerical order, not just how fast they clicked.
The data has to mean something educationally.
Right. When the data is interpretable in that way, the analysis results can directly inform design changes that genuinely enhance learning outcomes, not just gameplay tweaks.
Give us a concrete elementary classroom example here. How does this early stage analysis benefit the youngest learners?
Okay, imagine you're designing a simple digital alphabet tracing game for preschoolers. The focus is on fine motor skills and letter recognition. In the alpha stage, way before it's released, you collect basic data, where their little fingers move on the screen, where letters that get stuck on tracing, maybe the curves of an S are too tricky if they keep tapping a button that doesn't do anything. Basic visualization, maybe a simple chart showing time spent per letter, or a heat map showing the actual paths of their finger traces compared to the ideal path, immediately shows you what's intuitive and what's confusing for them.
You see where the traces go wild.
Yeah. Maybe you discover that preschoolers struggle to find the next letter button if it's tucked in a corner, or that their fine motor control just isn't developed enough yet for a very complex letter shape you designed. This instant visual feedback lets you fix those fundamental design flaws really early, ensuring the game actually measures letter formation skills, rather than just measuring how good a child is at fighting a clunky interface. It makes the game usable and effective for tiny hands.
That makes perfect sense. Fix the foundational stuff first so the learning can actually happen. Now, once the game mechanics are more solid, those initial kinks are worked out, we move into the beta development phase. How do our superpowers evolve here? What deeper insights do we get?
In the beta phase, things get more sophisticated. As the game mechanics stabilize and the core design is more robust, we move towards getting deeper insights, using primarily structure discovery and relationship mining. The focus shifts to understanding player decisions and learning patterns on a much deeper level. We're moving beyond just initial interactions to analyze how players are truly engaging with the learning content and whether they're developing the strategies we hoped they would. The X-ray vision starts discerning more complex patterns now.
Okay, so if alpha is about fixing the obvious mechanical or usability issues, beta is more about really understanding how students are playing, why they're making certain choices, and critically, if those choices are leading to genuine learning and understanding.
Precisely. This stage moves beyond assuming players will follow the ideal path the designers envisioned. It helps designers see how players organically explore and solve problems within the game's environment. And then, crucially, they can refine the game to better support those actual play patterns that still lead to successful learning. It's about observing reality and adapting the game to it, optimizing the learning path, not just fixing bugs.
Can you build on our previous elementary examples? Show how these methods might refine, say, that fractions game or the circuits game during beta.
Sure. Let's go back to that fractions game. After initial visualizations and alpha fixed obvious interface bugs, maybe during beta testing, cluster analysis, that structure discovery method, reveals something interesting. It might show distinct groups or clusters of students using different strategies. Maybe one cluster gets answers right, but the data shows they're relying purely on visual pattern matching of fraction shapes, not actually engaging with the numerical representations. They haven't grasped equivalence conceptually.
Ah, so they found a workaround that bypasses the real learning goal.
Exactly. That insight, uncovered by clustering the play data, could lead the designers to revise the game. Maybe they'd introduce levels that require numerical manipulation, or minimize the reliance on purely visual cues for certain concepts, make it harder to succeed without understanding. Or, using sequential pattern mining from relationship mining, designers might discover that students who struggle with a specific tough concept, say, subtracting fractions with unlike denominators, consistently follow a particular unproductive failure trajectory.
A sequence of actions that reliably predicts they're going down the wrong path.
Right. The sequence might involve things like trying random operations, repeatedly clicking the wrong denominator, maybe switching to multiplication by mistake. Seeing this pattern allows designers to add specific scaffolding, hints, or maybe a quick explanatory pop-up at the precise moment in the game when these unproductive sequences typically begin. It guides students towards more effective strategies just when they start to stray, leading to deeper understanding and helping refine the game's adaptive leveling.
So it's not just about getting answers right anymore. It's about ensuring they're using effective, conceptually sound strategies. This level of data insight allows for pinpointing those learning roadblocks with incredible precision.
It really does. It moves toward supporting the process of learning, not just the product.
That's a huge step forward for truly responsive, adaptive learning. Okay, finally, we get to the late beta and final release stages. You said this is where it gets really interesting for the individual learner, truly speaking to personalized learning. This is where our X-ray vision becomes predictive, right? Almost like a sixth sense.
It absolutely does. In these later stages, the core focus often shifts heavily towards predictive modeling. We're using the data collected from lots of players to build models that can identify key predictors of behavior and learning in real time. The ultimate goal here is often to enable real-time detection of student states. Are they confused? Bored? About to succeed? Which then drives truly adaptive, personalized game progression for each individual child.
So the game is actively anticipating student needs moment by moment, like having a personal digital tutor embedded right inside the game.
That's the aspiration, and it's becoming increasingly achievable. This phase allows for highly individualized learning paths based not just on past performance, but on predictions about future performance and current state. For an elementary classroom, this can manifest in several incredibly powerful ways.
Okay, paint us a picture. Give us some examples of how this predictive power plays out in a game designed for young children.
All right. First, think about adaptive scaffolding. We touched on this, but prediction makes it smarter. Imagine that science game again. Maybe now they're doing virtual experiments, mixing safe chemicals to see color changes or reactions. Based on a student's current actions, the sequence of chemicals they're picking up, the equipment they're selecting, the game's predictive model might forecast that they are about to make a critical error, like adding way too much of one region or missing a key observation step.
It sees the mistake coming before it even happens.
It anticipates the likely outcome of their current trajectory. The game can then offer just-in-time scaffolding. Maybe a subtle hint pops up. Are you sure you need that much?
Yeah.
A key piece of equipment glows briefly, or maybe it even dynamically adjusts the next step or provides a quick mini tutorial tailored to that predicted struggle. The student gets support before they fail significantly, preventing frustration and keeping them engaged in productive learning.
That's amazing. What else?
Second, we have behavior detectors. These are essentially real-time classifiers running within the game, trained to identify specific learning behaviors or even affective states based on gameplay patterns. For example, a detector could identify productive failure, that state where making mistakes is actually a healthy and necessary part of exploring and learning.
So the game knows when struggling is actually good.
Exactly. If the game detects a child is engaged in productive failure, they're experimenting, trying new things, learning from errors but staying engaged, it knows not to intervene immediately. It lets them keep exploring. Conversely, detectors can also be trained to identify states like boredom or confusion, maybe based on patterns like prolonged inactivity, erratic clicking, or repeatedly moving items off screen. If a game detects a child is likely bored, it could dynamically shift to a more engaging activity, maybe introduce a new challenge or offer a brain break to recapture their attention.
Wow, so the game adapts not just to their knowledge, but to their state of mind.
That's the goal. It allows for incredibly nuanced responsiveness, which is so important for maintaining motivation, especially in elementary learners who can disengage quickly.
That's fascinating. And what about personalizing the actual learning content they see? That sounds like the holy grail for differentiation in a classroom.
That's the third major application: personalized content delivery. Imagine a language arts game for, say, third graders, focusing on grammar, maybe parts of speech. Based on ongoing predictive analytics, the game might determine that a particular student is consistently struggling with identifying verbs within sentences. It could then dynamically adjust the game for that specific student. Maybe it starts generating new sentences with a higher density of verbs for them to practice identifying. Or perhaps it subtly changes the game's narrative prompts to include more opportunities for verb usage and identification.
And the student might not even realize it's remediation.
Ideally, no. It just feels like part of the game flow. This moves way beyond simple pre- and post-tests. It allows for what the source calls process-based assessment, tracking how a student's understanding evolves moment to moment within the task itself, rather than just judging their final score. It truly tailors the learning experience to each unique individual, fostering genuine mastery at their own pace.
It's really clear that learning analytics, applied thoughtfully to serious games, has this immense potential. It can advance learning theory itself, but also provide very practical, data-driven design principles for creating these engaging, personalized experiences. This means games aren't just fun anymore. They're becoming these powerful learning environments that can respond to your students, the kids in your classroom, in ways never before possible. Fostering that interest-driven learning we all strive for, it's truly bringing our X-ray vision to bear on the entire learning landscape.
You've captured it beautifully. And games offer a unique opportunity for assessment that goes far beyond traditional multiple-choice tests or worksheets. Because students explore, experiment, and test boundaries within a game environment, trying different strategies, making mistakes, iterating these rich emergent player patterns can be mined for insights.
So the way they play is the assessment.
It can be a significant part of it, yes. This complements traditional assessments by allowing for more rigorous measurement of complex competencies. Things like problem-solving strategies, critical thinking, maybe even collaboration in multiplayer games, not just recall of facts or final answers. It offers a much more authentic and comprehensive view of a child's capabilities as they're actually applying them.
So how might this change the way elementary teachers think about assessing those really tricky skills, like collaboration or creative problem solving in a digital environment? These are often so hard to measure precisely in a traditional classroom.
Precisely. Instead of just relying on a subjective observation or a rubric score that might miss nuance, imagine having data-backed insights. You could potentially see how a student collaborates in a group game. Who do they interact with most? How do they contribute ideas? How does the group recover from a failure based on communication patterns? For creative problem solving, you can measure how they innovate within the game's rules, the novelty of the pathways they try, the originality of the solutions they discover when faced with an open-ended challenge. This opens up entirely new avenues for understanding and supporting student growth in these vital 21st century skills. It provides concrete evidence for areas previously left largely to intuition.
That's potentially transformative for how we understand student abilities. Looking ahead now, what are the biggest challenges and opportunities for the future of game-based learning, especially with these powerful analytical tools?
Well, one major opportunity definitely lies in technological advancements. The rise of more immersive technologies, 3D environments, augmented reality, AR, virtual reality, VR games, will only increase the richness and dimensionality of the data we can capture. Imagine the depth of insight you could gain from analyzing a student's interactions as they navigate a fully immersive VR learning environment, maybe dissecting a virtual frog or exploring ancient Rome. The data streams will become even more granular, more complex, requiring even more sophisticated analytical tools, but potentially offering unprecedented insights into learning processes.
More data, more potential insight. And you mentioned earlier this fascinating convergence happening between commercial games and learning games. That seems like a huge opportunity too, right? Bringing entertainment quality to education.
Yes, this is a really significant trend and opportunity. We're already seeing widely used subscription model learning games, things like ABC Mouse or ST Math, that integrate sophisticated data collection and analysis. Beyond that, popular commercial games are being modded or officially adapted for educational purposes. Think SimCity EDU or educational versions of games like Minecraft or Plants vs. Zombies. And then there's what's called tangential learning, where the inherent engagement of commercial giants like Minecraft or Civilization is leveraged as a vehicle for learning specific concepts, and increasingly, data can be extracted even from those experiences to assess learning.
So a teacher might actually use data from students' Minecraft builds to assess their spatial reasoning or collaborative planning skills.
Potentially, yes. Frameworks are being developed to do just that. It means the polished design, the deep engagement, the qualities of games your students already love are increasingly being brought into the learning space. And crucially, they're backed by powerful data analysis to ensure learning has happened effectively. That's a potent combination for keeping elementary students deeply engaged.
A winning combination indeed. But surely there are challenges too. It can't all be smooth sailing.
Oh, definitely not. A significant challenge, which is also an opportunity for innovation, is the need for robust, well-designed data frameworks. The source really emphasizes this. Clearly structured, comprehensive learning data is key. Building this framework early in game development, ensuring you're collecting the right data in a clean, usable format is absolutely crucial. But it can be technically challenging and requires careful planning from the outset. If the data isn't collected well, if it's messy, incomplete, or not aligned with learning goals, even the most sophisticated analytics won't yield meaningful insights. Garbage in, garbage out, as they say.
So the foundation of data collection has to be solid.
Absolutely. Like building a house, the foundation is critical. And another related point is about the development process itself for learning games. Is there a push for them to be built more like top-tier commercial games, using similar methods? Yes, there's a strong call to action within the field for the learning game industry to more fully adopt commercial game development best practices. This means embracing iterative, user-centric design. The mantra in commercial games is often fail early and often, using frequent playtests, gathering user feedback constantly, and iterating rapidly based on both qualitative observations and quantitative data analysis, like we've discussed. This commitment to continuous improvement, so common in the commercial world, is vital for creating higher quality educational products. Products that are not only effective but also genuinely compelling, maybe even game students would choose to play voluntarily outside of school because they are that engaging.
Which raises a really exciting thought, doesn't it? What if the next big breakthrough in elementary learning games comes from a small, agile team that perfectly integrates these analytics into a truly captivating, maybe even beautiful game experience, making learning genuinely irresistible?
That's the dream, isn't it? It could democratize access to highly personalized, deeply engaging education on an unprecedented scale, reaching every child with precisely the support or challenge they need exactly when they need it, all wrapped up in an experience they love.
That's a powerful vision. Okay, let's try to wrap this up. What does this all mean for us, especially for educators listening? We've seen how learning analytics and educational data mining are giving us this incredible insight, this X-ray vision, into how students interact with games. From predicting challenges before they happen, to uncovering hidden learning strategies, to literally visualizing their learning journeys. These tools are fine-tuning digital learning experiences like never before.
That's right. By leveraging comprehensive data and applying these 5 powerful analytical methods, prediction, structure discovery, relationship mining, discovery with models, and visualization, game designers can craft learning experiences that are highly personalized, deeply engaging, and demonstrably effective. They can do this across every stage of the development cycle, constantly improving.
And for you, our listener, maybe an elementary educator just starting to explore game-based learning, understanding these methods isn't just, academic jargon.
Not at all.
It's about knowing what makes a truly powerful educational game tick. It helps you evaluate the tools you might use in your classroom. And maybe it even gets you thinking differently about the data you can get from simpler digital tools you already use.
Yeah.
How you might use that information to better support your students' individual growth and provide that personalized attention they deserve.
Well said. It empowers educators to be more informed consumers and users of these increasingly sophisticated learning technologies.
So here's a final thought to leave you with. Given this immense power of data, this X-ray vision, to understand and adapt to how every single student plays and learns within a game, what new possibilities does this open up for your future classroom? How might this kind of insight shape the next generation of truly transformative learning experiences for young children, helping every single child find their own unique path to understanding and ultimately unlocking their full potential?